Turkey. This is Professor Ece. Okay. This is Professor Ece Yetkin Celikel. And the talk it is observing ideal structures of commutative ring space.
Okay, I will start. So
yeah,
I'm
sure.
one of the, first of all, I want to let me introduce myself. I'm one of the ex-PhD student of Professor Ünsal Tekir. And first of all, I want to thank to him and to all of you for giving me this opportunity to present this type of structures of commutative rings, which I love them very much. And I am from Hasan Kalyoncu University from Gaziantep, Turkey. And first of all, I want to show you where I am here. Now you are in some located here, Sofia. And here is our beautiful, gorgeous city, Istanbul. Professor Ünsal Tekir, Professor Bayram Ali Ersoy, and also our colleagues, Eda is located there. And the capital of our country is Ankara. And if you go southeast of Turkey, then you can see SP, Gaziantep. And this city is the economic center of the southeast of this Turkey. And also there are historical places, museums, and please, if you love eating, then we have lots of traditional, world famous foods, Turkish foods. So all of you invited to Turkey, and especially in Istanbul, and of course, Gaziantep. Then I will turn back our work, and I want to show you first the references, which I used all of them in this preparing these slides. So first of all, everything begins with prime ideals, okay? Every structure in here depends on prime ideals. Every algebraist can confess that prime ideals have an essential role in commutative ring theory. That's why lots of researches are done for generalizing this concept. One of the generalization of this concept is two absorbing primary and two absorbing ideals, which is introduced by Ayman Badawi in 2007. Then my advisor, Ünsal Tekir, and Badawi gave the definition of two absorbing primary ideas, generalizing the first one, the previous one. Then one absorbing primary ideas are studied, which is a subclass of the previous one. Then we extend this idea. This is in the commutative ring. And if you extend this idea to submodules, then you can get the other definition. And lastly, I will show you some applications of these ideas to graph theory, okay? So here are very basic notations I will use. R will be a commutative ring with non-zero identity. The R will be the set of all zero divisors of this ring. And I will be a proper ideal of R. And the radical of I will be, as usual, the intersection of the all prime ideals which containing I. So this one equals, in the commutative ring, of course, this sets all elements of R and whose some positive power will belong to I. So let's start with recalling the definition of prime ideals. As everybody knows, a proper ideal P is said to be prime if whenever you have two elements in here whose multiplication in the ideal P implies that one of the elements belongs to P. So, in the other words, can we say that if P is prime, then P absorbs one of the elements, okay? So, for a minute, just think that this idea can be generalized to three elements now. If you have three elements, for example, A, B, C, whose multiplication belongs to I, then it implies that one of the double products, AB, AC, or BC, belongs to I. Then he said that, Ayman Badawi, said that I is called two-absorbing ideal if it satisfies this condition. So, just looking at the definition, every prime will be two-absorbing, but the converse of this relation is not true in general. You can consider this example here. I is 6z in the ring of integers. So this is two-absorbing ideal. We can share the general theorem for saying that it is two-absorbing ideal later. But this is two-absorbing, which is not prime. You know, 2 times 3 is in here, but neither 2 nor 3 is the element of this ideal. So recall primary ideal now. If I is said to be primary, if whenever 2 elements A, B, whose multiplication belongs to I, implies that one of them, A, it belongs to I, or the other one should be in the radical. So now think the generalizations of this ideal now. So we can call I is two-absorbing primary if you have 3 elements again, whose multiplication belongs to I, implies that one of the double production A, B belongs to I, or if it is not, the other double products should be in the radical. Now, you can see from the definitions directly, two-absorbing primary ideals are both generalizations of primary and two-absorbing ideals, but the arrows are irreversible. So you can consider this example for showing that this is a counterexample for these implications. For example, I is 12z in the ring of integers z, and this is two-absorbing primary. I will share the proof and the theorem later, but it is not two-absorbing. Why? 2 times 3, this is 12. This is the element of I. So you have these productions, 2 times 2. It is not in this ideal. And also 2 times 3, 6. This is not in this ideal. So that's why this is not two-absorbing. So we can compare all of the structures from now. Prime, primary, two-absorbing, and two-absorbing primary structures. There are some picture here. All prime ideals in this ring are produced by some prime integers, you know. And primary ideals are characterized by this one. And what about two-absorbing and two-absorbing primary ideals? Now we can get some characterizations, and I will show you the general theorem again. Two-absorbing ideals are in this type, p square, or p times q, where p and q are distinct prime integers. And now if n and m are positive numbers, then two-absorbing primary ideals can be characterized by this form. So if you know it, in the commutative algebra, if you have a primary ideal and take the radical, then you get prime ideal. Now, a similar relation exists here. If I is two-absorbing primary and take the radical is two-absorbing, okay? And one of the following statements must be hold. The radical can be prime, or the radical can be intersection of 2 minimal prime ideals. But the converse is not true in general. So it means being the radical two-absorbing does not imply that I is two-absorbing primary. And here is the example. You can consider the polynomial ring on the ring of integers. X, Y, Z are indeterminates, and let I is in this form. Then the radical will be two-absorbing, but I is not two-absorbing primary. Because of this element, X, Y, Z is the element of I, but neither xy belongs to I, nor yz or xz belongs to the radical. So this is not to absorbing primary, but radical to absorbing. So the next theorem gives you the equivalent statements. Now this says that we can define two absorbing primary ideals in terms of the elements of R, or you can use some ideals of R instead of the elements. You can change the elements by ideals. Okay. So now, as a recent research with Badawi, in this year, we call I is one absorbing primary ideal. This is a subclass of two absorbing primary. If you have 9 unit elements here, A, B, and C, and whose multiplication is belong to I, then it implies AB belongs to I or C belongs to the radical. And Yasin et al., 1 year later, said that I is said to be one absorbing prime ideal of the ring if you have this condition, just interchanging the radical by the I itself. So every one absorbing prime ideal will be one absorbing primary, of course, but the converse is not true. And I want to show a big picture for you, which contains all of the relationships from now. Prime, one absorbing prime implies that two absorbing and two absorbing primary. Or you can choose the other way. Prime, primary, one absorbing primary, and two absorbing primary. And all of the numbered arrows are irreversible. We have these examples, these counterexamples, to show that the converses are not true. You can see this example from this paper, and R will be z plus 3x dx, and you can consider this prime ideal. Then you can see P squared is two absorbing. It is two absorbing because of the Badawi's paper. It satisfies some conditions in here, but P squared is not one absorbing prime. Now, as you can see, 3 times x squared is the elements of P squared. This is 9x squared, and this belongs to P squared here. But 3, 3, 9 does not belong to P squared, and x squared does not belong to P squared again. So what about the other example? Now you can consider the ring of integers and the ideal 12R generated by 12. So this is two absorbing primary. Because of this principal ideal domain, I will give the general theorem for it. But this is not one absorbing primary. Just indeed 2 times 3, this is 12, element of I, but neither 2 times 2, this is 4, element of I, neither nor 3 elements of the radical. This is 6R, of course. Now, we gave a method for construct one absorbing primary ideals, but they are not primary here. If you consider a quasi-local ring with a maximal element, with a maximal ideal, and take an element from this maximal ideal, which is non-zero and prime, which satisfies this condition, then Xm is always one absorbing primary ideal. That's not primary. So we can build this such example by using this method. So here is the application of this theorem. You can use this way in here. So the rest of the presentation, I want to show you some characterizations of one absorbing primary and two absorbing primary ideas in some special rings. And also, I will show you, we can characterize the whole ring by using just looking at these type of ideals. For example, if a ring admits one absorbing primary ideal that's not primary, then this is quasi-local. So, in the other words, as a corollary, we can say that R is not quasi-local, then one absorbing primary and primary ideals coincide, okay? So, as a conclusion of this corollary, if you write the Cartesian product of two rings, R1 and R2, and if you take a proper ideal, then we have this equivalent statements. J is one absorbing primary if and only if this is primary, because this is not quasi-local. And also, J can be written by I times R2 for some primary ideal, or J equals R1 Cartesian product L for some primary ideal L. This comes from just characterization of primary ideas. It have already known it. But in the case of two absorbing primary ideals is different here. If again you have Cartesian product of rings and you want to discuss all of the two absorbing primary ideals of this ring. So this is not same as primary ideas, and also this is not same as two absorbing primary ideas. Two absorbing ideals, okay. So if J is two absorbing primary ideal, you have two cases. J can be in this form, it should be in this form always, but IK is one of the IK, is two absorbing primary, and the rest of all of the ideals should be equal to the whole ring. Or two of them are primary, IK and IM, two of them are primary, and all other ideals should be equal to the whole ring. So I want to recall some definitions which I used in the next theorem. R is said to be divided ring if every prime ideal can be comparable with every principal ideal in this ring. Or in the other words, we can write this condition. And if two principal ideals, every two principal ideals can be comparable, then we can say that this ring is chained ring. And we have these implications between them. So what about the two absorbing primary and one absorbing primary ideas in these special rings? We can characterize them by this theorem. Every proper ideal of a divided ring is two absorbing primary. Now, I said before, every chained ring is divided. So in particular, every proper ideal is two absorbing primary also. And an integral domain, if it is also chained ring, then we call it valuation domain. So by this theorem, we can characterize all of the one absorbing primary ideals in valuation domains here. These are coincides, and it is in this form. Now, similar to this theorem, we will characterize all of the one absorbing primary ideas in peripheral domain also. And another characterization. Now, this theorem says that we can characterize all Dedekind domains just looking at the one absorbing primary ideals of this ring. If another proper ideal I is two absorbing primary, if and only if it is in this type, then a Noetherian integral domain is Dedekind domain. And the converse is also true. And what about the characterization of Dedekind domains in terms of now two absorbing? This is in terms of one absorbing primary. And this characterization is in terms of two absorbing primary ideas. Now we have this equivalent statements here. R is Dedekind domain if and only if I is two absorbing primary, then you have two cases. I can be in this form, m to the power n, where m is a maximal ideal, or I can be written as m1 to the power n, m2 to the power n. Since crude dimension is 0 here, so you can write it directly in this form, p to the power n, or p1 to the power n, p2 to the power n. You know, every principal ideal domain is Dedekind. So in particular, we have the same characterization for principal ideal domains. I is one absorbing primary if and only if I is in this form, where P is the prime element of this ring. And I is two absorbing primary. Again, we are in the principal ideal domain. Either I is produced by P to the power K or generated by P1 to the N, P2 to the N. For example, you can consider principal ideal domains, the ring of integers, or f of x. This is the ring of polynomials, and f is a field here. But there are some two absorbing primary ideals needs not to be the previous form. A two absorbing primary ideal here, you can consider this ideal, but this is not in this form, P1 to the n, P2 to the n. Because of this is not a principal ideal domain. This is a unique factorization domain at all. Now, you know, if the ring is Noetherian, then we have a primary decomposition in it. Every non-zero proper ideal has a primary decompositions. So we know all primary ideals are two absorbing primary. So we can say that every proper ideal has a decomposition into two absorbing primary, of course. But this decomposition is not unique. For example, if you consider this ideal, you have 4 distinct two absorbing primary decomposition. And if you consider the other ideal, you have exactly 10 distinct two absorbing primary decompositions here. And also, as I told you, I studied it in the module theory. And as a corollary of some result in this paper, I proved this theorem, one absorbing primary avoidance theorem for commutative rings, analogous to primary or prime avoidance theorem for commutative rings. If you have these ideals, such that at most 2 of them are not one absorbing primary, with satisfying I is subset of this union, then if this condition is satisfied, then we can say that I subset of one of the ideals. And now I want to mention some of the applications of this idea in the graph theory. As you know, Anderson and Livingston gave the definition of the zero divisor graph, gamma R, in 1999. And the vertex sets will be non-zero zero divisors, and they are adjacent to pair, this pair adjacent if and only if the multiplication of them is 0. Now, again, we will define triple zero graph. And what about the vertex set? The vertex set will be the triple zero elements. The triple zero elements can be defined by all non-zero zero divisors, and there exists some non-zero elements B and C, which makes it this production 0, but the double products are not zero. So we call it, this is 000 elements, okay? So this graph has this vertex set, and A and B are adjacent if and only if AB, AC, BC are not zero, but there exists an element C which satisfies this production is zero. So for example, there's a complete graph here, Z27. And there are some relations between this graph and this structure to absorbing ideal structure. And we have some results, but I want to show you just a summary of these results. We have this table for the 000 graph of Zn, and it depends on n values, the number of vertices, edges, and diameter and girth, and some results are contained here. And now you can see that there are more generalizing concepts and absorbing ideals are done, and weakly structures are studied. And also it is studied in multiplicative lattices. And then the related articles about them, the fuzzy of it is studied, and S extensions are studied also. And what's next? I want to thank to you, and if you interested in these type of structures, please contact me via this mail. It will be my pleasure to do any possible common work with you. Thank you. That's all.
Thank you very much for the talk. Do you have any questions or comments? You can ask directly, or you can make the comment directly. Okay, usually our talks, they are 40-45 minutes, but I didn't tell you that this is the normal way. So you decided to be faster than we expected.
Yeah.
Anyways, thank you very much.
You're welcome. I want to thank you.
Okay. I see that there are people in snow there. Bayram is
Can I ask a question? Can I
Yes.
ask a question?
Yeah, sure, you can ask.
We study also the same topic, but what about the daily life application of this topic?
Oh, it's very difficult question, you know.
Yes, I know.
I don't
Because
know.
in normally we are studying pure algebra.
Yes.
The general question is, what about the daily life application do you have? I can say always no, I don't know. But do you have?
I don't know also. It is
There is
very difficult. It is very terrible question for studying pure mathematics. If you're studying in pure mathematics, everybody asks this question, but I cannot answer it.
You see, in the 60s, we had a professor, and in the question where you are going to apply your results, the results for my promotion. So
always the same
have an
question.
application.
Always the same question we have.
This is a question which undergraduate students are too shy to ask. And indeed, they are given only stuff that really has, well understood applications. And then when you are no longer students, it's too late. Nobody to ask. Yeah. My question is, I have some stock questions. Is the first order theory of this class of ideas decidable? Are there some algorithmic results? For instance, can I decide whether the membership of some terms in an ideal implies the membership of some other terms, or a disjunction of these, something like that?
I cannot understand.
So the question is, you have an explicitly given ring. And the question is, are you able to, for example, to recognize whether an idea is from your class or not?
Yeah. Or whether given
explicitly.
the idea is in this class, whether a certain term belongs to it, say, given in the generating elements, say, the term or something like that. So are there algorithmic results about this class of ideas in general?
No, I don't have any algorithmic results in here, but I can think about it. Thank you.
So, for example, if you have some big N, can you describe all the ideas you need from your classes if you work modulo N?
Yes, of course. For example, okay, I need to share slide again. Where is it? For example, you mean in the ring Zn or Z, just that, or Zn, how big n can be? It is principal ideal domain. And we can find all of the absorbing ideals by using this one, I equals p to the power k, just prime ideals and the powers. So again, two absorbing primary ideals can be written as prime ideals to the powers, or two prime ideals to the n and m. I see, we can count them. You mean, can we count them? How many one absorbing primary ideas and how many two absorbing primary ideas? Of course, it can be written an algorithm for count all of the one absorbing ideas and all of the two absorbing ideas by using just this way.
Okay, thank you.
Okay.
Some other questions or comments?
Yes, Professor, if I can.
Yeah, sure.
So my question is not a question, but I noticed something. For example, if we have a commutative ring and we have an ideal which is two absorbing primary or one absorbing primary. So is this characteristic can be transposed to the factoring ring? For example, if I form the factoring ring R over I, if I is containing in the two absorbing ideal primary ideal, so is P over I is again two absorbing primary or one absorbing primary? So
yes.
that means, yeah.
Yes, of course. If you have an epimorphism here from R to R over I,
Yeah.
so these structures are saved here, okay? If there is some ideal here, J is two absorbing, then J over I will be also two absorbing. It is saved. Okay. These behaviors are all studied in these papers. For example, homomorphic images, localizations, and the other properties of them.
Yes, why I ask that, because some characteristic of some kind of ideals cannot be transposed from a ring to another ring. For example, maybe the inverse or the converse of this thing is not work. Maybe for example, if we have two absorbing primary ideal in the factoring ring, maybe the ideal in the original ring is not two absorbing primary.
But it is saved here.
I see. Thank you.
Okay, welcome.
Some other questions? Okay, if no other questions, you see, usually we post the presentations in the homepage of the seminar, and we also post the video. So if you agree, you will have your video in our seminar. And also, yes. I will be thankful if you send me the presentation, and we will post it.
Okay, it's okay for me. Thank you.
Okay. You'll be a movie star in YouTube.
Okay, thank you.
And now you
Enjoy
can
him.
speak
Thank you.
in any language between them. Bulgarian, Turkish, or English, or what you want.
Okay, I will
Teşekkür ederim.
I'll now
In
stop
Turkish.
recording, and
Yeah.
you can use the rest of the time for an informal discussion. Just have a chat, please. Yeah, using Zoom.